Have you ever looked at advanced trigonometry and just thought, it's an endless list of formulas to memorize? Well, today we're going to change that. We're going to tackle some really tough trig, not by memorizing, but by building the ultimate trig toolbox.
On deriving the Pythagorean trigonometric identities, we will be answering a question from the mathematical logbook. We will derive three key identities: the fundamental identity, which relates sine and cosine, and two others relating tangent and secant, and cotangent and cosecant. Start with the foundation, the Pythagoras theorem. Consider a right-angled triangle with sides A, B, and hypotenuse h. The theorem states that a squared plus b squared equals h squared. The first derivation starts with the Pythagoras theorem. By dividing all terms by h squared and recalling the definitions of sine and cosine, we derive the fundamental identity. Cosine squared a plus sine squared a equals 1. To derive the second identity, start with the fundamental identity and divide all terms by cosine squared a. After simplification, we get 1 plus tangent squared a equals secant squared a. For the third derivation, we again start with the fundamental identity. This time, we divide all terms by sine squared a. Recalling the definitions for cotangent and cosecant, we get 1 plus cotangent squared a equals cosecant squared. In summary, we have successfully derived the three Pythagorean trigonometric identities: the fundamental identity, and the identities relating tangent and secant, and cotangent and cosecant.
So you look at an equation like this, and yeah, it looks pretty intimidating, right? Your standard tricks, sine squared plus cos squared equals 1, they're not really going to help you here. It just feels stuck. But what if I told you there's a tool designed specifically for this exact situation? And that's really the whole idea behind this explainer. Forget just learning things by rote. Instead, we're going to build a really powerful trig toolbox together, one tool at a time. And by the end, you'll see how having the right tool for the job makes even the toughest looking problems just fall apart.
Finding the roots for the quartic equation, 8 cos to the power of 4x negative 10 cos squared x plus 3 equals 0, within the range 0 degrees, is less than or equal to x is less than or equal to 180 degrees. The problem is a quartic equation in terms of cosine. To solve it, we will use substitution to transform it into a more manageable quadratic form. Step 1 is the substitution. We let y equals cos squared x. This reduces the degree of the equation by half, rewriting the original quartic as the quadratic equation 8y squared dash 10y plus 3 equals 0. Step 2 involves solving the quadratic equation to find the values of y. We identify the coefficients as a equals 8, b equals minus 10, and c equals 3, and then apply the quadratic formula. Applying the formula, the discriminant is 4, and its square root is 2. The primary calculation results in 12/16 and 8/16 for the two roots of y. Step 3 is finding the roots of y. Simplifying the fractions, the two roots are y1 equals 12/16 or 0.75, and y2 equals 8/16 or 0.50. We must now use back substitution to find the values of x. For case study 1, we reverse the substitution for y equals 0.5, meaning cos squared x equals 0.5, or cos x equals plus or minus square root 0.5. Within the range 0 degrees to 180 degrees, cosine is positive in quadrant 1 and negative in quadrant 2. For the positive root in quadrant I, cos x equals plus square root 2 halves, which gives x equals 45 degrees. For the negative root in quadrant 2, cos x equals square root 2 halves, which gives x equals 135 degrees. Case study 2 is y equals 0.75 or 3/4. This means cos x equals plus or minus square root 3/4, or plus or minus square root 3 halves. This will reveal the remaining angles within our specified range. For the positive root, cos x equals square root 3 halves, which results in x equals 30 degrees. For the negative root, cos x equals square root 3 halves, resulting in x equals 150 degrees. In summary, we substituted to convert the quartic to a quadratic, solved for y, reversed the substitution to find cos x, and identified the final solutions for x as 30 degrees, 45 degrees, 135 degrees, and 150 degrees.
These looking problems just fall apart. Okay, let's open up the toolbox and grab our very first tool, the compound angle formulas. So what do? Well, their main job is to help us deal with expressions that have a sum or a difference of two angles, like a plus b or a minus b. They let us either expand them out or combine them together.
Solve the equation 5 cos squared 3 theta equals 3, 1 plus sine 3 theta. The problem is to solve the given equation for the interval, where theta is between 0 degrees and 90 degrees, inclusive. First, we use the identity cos squared x equals 1 dash sine squared x to express the entire equation in terms of a single trigonometric function, which is sine. This substitution transforms the equation to 5 to 5 sine squared 3 theta equals 3 plus 3 sine 3 theta. Next, we perform a quadratic transformation by rearranging the terms and setting the equation to 0. 5 sine squared 3 theta plus 3 sine 3 theta 2 equals 0. By letting x equals sine 3 theta, we get the standard quadratic form, 5x squared plus 3x negative 2 equals 0. We will now solve the resulting quadratic equation by applying the quadratic formula. Using the quadratic formula with the positive discriminant, we find the first root for x. Substituting a equals 5, b equals 3, and c equals minus 2, we get x equals 0.4. This means sine 3 theta equals 0.4. Using the quadratic formula with the negative discriminant, we find the second root. This calculation yields x equals minus 1.0. Therefore, sine 3 theta equals minus 1. The back substitution steps involve using inverse sine to find the basic angles for 3 theta, checking all possible angles within range, dividing by 3 to find theta, and validating that theta is between 0 and 90 degrees. We summarize the solutions. For sine 3 theta equals 0.4, the final valid values are 7.86 degrees and 52.14 degrees. For sine 3 theta equals minus 1.0, the final valid value is 90 degrees. The final solution set for the trigonometric equation within the defined interval is theta equals 7.86 degrees, 52.14 degrees, and 90 degrees. These angles satisfy all constraints.
You know, it's one thing to have a formula, but it's way more powerful to understand where it comes from. Take the formula for tan A minus B. It's not magic. You just start by rewriting it as sine over cosine. Then you expand the top and bottom using the formulas we just saw, and then you do one clever little division, and boom, everything turns into tangents. It's a completely logical process. All right, tool number 2. This one tackles one of the most common places people get stuck in trig, when you're just left with sums. You've got something like sin of A plus sin of B, and you can't simplify it any further. You need a way to transform it, and that is exactly where the factor formulas come in. So what's the big trick with the factor formulas? They turn a sum into a product. Now, why is that so useful? Well, think about it. When you're solving an equation that's equal to 0, a product is your absolute best friend. Because if x times y equals 0, then you know that either x is 0 or y is 0. This tool lets us do that exact thing with trig expressions. And hey, don't just take my word for it. This quote from our source material absolutely nails it. The whole point is factorization. It's about taking an expression that's stuck together with a plus or minus sign and breaking it into these neat, manageable pieces that are multiplied. It's a fundamental algebra trick, just applied to trig. All right, time for a very specialized tool. This is the R formula. You pull this one out of the toolbox whenever you see a sine and a cosine of the exact same angle being added or subtracted, just like in that challenge problem from the beginning. And the idea behind it is this really brilliant bit of geometric thinking. The R formula takes that messy sum, A cos theta plus B sine theta, and it asks you to imagine those numbers, A and B, as the two shorter sides of a right-angled triangle. This amazing little trick lets us combine both of those terms into a single, clean sine or cosine wave. Okay, so how do we actually find the parts of this new function? Well, the new amplitude, which we call R, that's just the hypotenuse of our triangle, so we find it with Pythagoras. And the new angle shift, we call that alpha, you just find it using the tangent of B over A. It's such an elegant connection between the algebra and the geometry.
Before we continue, remember to subscribe to The Backbencher and drop a comment below. Your feedback helps shape the next lessons and keeps this learning community growing. We'll begin with phase 1, the transformation. Our goal here is to express the expression 7 cosine 2 theta plus 6 sine 2 theta in the form r cosine 2 theta minus alpha, where r is our amplitude and alpha is our phase shift. To start, we use the cosine subtraction formula as our template. By expanding r cosine 2 theta minus alpha, we can see exactly how the r cosine alpha and r sine alpha components align with our original numbers. By comparing the two sides, we establish two vital relationships. R cosine alpha equals 7 and R sine alpha equals 6. Think of these as the horizontal and vertical components of a vector
And
with
now,
length r.
for our final tool. If the R formula was a specialized key, I want you to think of the T formulas as the master key. This one is, honestly, it's unbelievably powerful because it does something incredible. It converts tricky trig problems into pure algebra. So how does it work? Well, the entire method hinges on this one incredibly clever substitution you see on the slide. We just invent a new variable, t, and we set it equal to the tangent of half the original angle. Now, I know that might seem a little strange at first, but just watch what this lets us do. Because of that one little substitution, we can now write expressions for sine, cosine, and tangent of the original angle entirely in terms of our new variable t. And just like that, poof, there's no more trigonometry. It's all just rational expressions from algebra. I mean, that's the magic of the t formulas right there. So we did it. We've built our toolbox, we've got our compound angle formulas, our factor formulas, the R formula, and now our master key, the T formulas. So let's go all the way back to that problem from the beginning and see how our new set of tools makes it completely manageable. Here it is again. 7 cos theta plus sine theta minus 5 equals 0. The problem hasn't changed one bit, but we now have a full toolbox. And for this job, we are definitely pulling out the master key. The process is really systematic. First, we just swap out cos theta and sine theta with their T formula versions. Okay, it looks a little messy for a second, I'll admit. But then we just multiply everything by that denominator, 1 plus t squared, to get rid of the fractions. And finally, we just clean it up. We collect all the like terms. And just look at what we're left with. No more sines, no more cosines. That problem that looked so intimidating has been transformed into a simple quadratic equation in T, an equation that every algebra student knows exactly how to solve. That is just an amazing transformation. And that really is the big takeaway here. What seemed impossible is now just algebra. It wasn't about being some kind of trig genius, right? It was just about knowing which tool to pull from the toolbox and knowing how to use it. So, the next time you face a tough equation, don't just see a problem, see an opportunity to choose the right tool. Now that you have this toolbox, what other impossible problems are you going to be able to solve?